Welcome back to this final lecture in the Programming Languages series. Today we're going to have a look at visual programming and the various tools and languages that have been developed over the years. The outline today looks like this. First we'll have a quick look at some basic terminology, then we'll have a tour of various languages and systems that have been built over the years. Then we'll try and step back and see what we can learn from this and try and motivate the need for better taxonomy and understanding of visual programming languages. Finally, we'll have a closer look at eToys, which is a very nice and sophisticated visual programming tool that's been developed in Scratch. I'm using various sources. As you may notice here, a lot of these sources are quite old. Surprisingly, there hasn't been an up-to-date survey that's been produced in the last 20 years or so. So the state of the art in terms of literature is rather out of date. Surprisingly, one of the best sources nowadays is Wikipedia. So what exactly is visual programming? I pulled out three definitions here. They don't give us a great deal of insight, however. So a very old definition from Myers basically says that we can, in visual programming, you specify a program in 2 or more dimensions. Fine. Burnett in 1999 says visual programming is programming in which more than one dimension is used to convey semantics. Also, not very deep. And Wikipedia goes a little bit further. This is a definition from 2008 that visual programming is any language that lets users specify programs by manipulating program elements graphically rather than specifying them textually. So this goes a little bit further in the sense that it talks not just about the graphical display, but also the interaction, so the act of manipulating program elements. Nevertheless, this doesn't give us a deep insight to actually what different kinds of visual programming paradigms there are. Let's have a quick tour through history to see what people have done with visual programming languages. Going far back in time, back in 1963, this is not a visual programming language, but this is the first time that a computer system has been developed with a graphical user interface using an XY plotter and a light pen to construct two-dimensional graphics. This was Ivan Sutherland's Sketchpad system, which was highly influential. The first programming by visual programming language that I'm familiar with is known as Pygmalion. This comes from the mid-70s. And this was not just a visual programming system, but a so-called programming by example system. Here the idea is that you specify a program interactively by showing examples of what the result should be. So in this particular example, we want to teach Pygmalion how to compute factorial. So in this particular case, we tell Pygmalion that we want to compute factorial of 6, so we draw a 6 and we draw an exclamation mark, and then we explain to Pygmalion that if this value 6 is equal to 1, then we do one thing, and if it's not, then we have to compute 6 minus 1, so then we have factorial of 5. So Pygmalion then learns to decrement the argument to the factorial, and then it will learn to recurse. Eventually, it finds out that the value that we want to compute the factorial of is 1, but it doesn't know what that value is, so finally we teach it that, and then Pygmalion knows everything that it needs, and it finally computes the value 720 for 6 factorial. We'll see a more advanced tool in a few minutes, which is based on so-called graph grammar. So that's takes this idea of programming by example and instead casts it into the formal framework of graph rewriting. Still fairly early on, the alternate reality kit was developed in the 1980s. Here, the idea was, instead of manipulating graphs or trying to compute functions, the idea was to really exploit the two-dimensional environment for creating simulations. So the idea is that you would build physical simulations of objects and give them properties that allow them to react according to physical laws. Since that time, there have actually been a number of applications built for kids to help children learn about physical laws and chemical laws and so on. So basically graphical simulation environments. So this idea is quite popular, but has been used especially in the area of teaching. Still fairly early on, this is the late 70s, ThingLab was a graphical constraint satisfaction system that was implemented in Smalltalk by Alan Borning. So in this system, we can link two visual displays of a thermometer, one in Fahrenheit and one in Celsius, and connect them with nodes that represent various operations and constraints. The interesting thing about this particular tool is that the constraints, of course, work in two directions. So it's not a procedural system, but it's actually a constraint-solving system. So that means when you grab the thermometer in Celsius and twiddle it, then you'll get the values in the other thermometer being adjusted and vice versa. A little bit later, Fabrique was a similar kind of tool, except instead of being based on constraints, it was based on bidirectional data flow. So here's a similar example from 1988, where we have Fahrenheit and Celsius thermometers, and they stay in sync, but instead of using constraints, these bidirectional data flows will cause events to flow from one component to another. Starting in the late 80s, early 90s, there was a lot of interest in using visual paradigms for displaying the architecture of software systems. So-called architectural description languages, some of which were textual and some of which were visual, try to break down a high-level view of a software application, a software system, in terms of high-level components and connectors that allow you to connect the services of these components. Notice that what a component is generally undefined. So a component can be something relatively small scale, as small as a class or a package, but more typically it's a larger thing like a subsystem or a high-level component. We speak of architecture because in the context of architecture you want to reason about the high-level components of a software system and the constraints that govern them. So architectural constraints limit and control how you can manage the high-level structure of an application. Examples for a typical example is a layered architecture in which the components are layers and the constraints are that communication always flows down, so you only speak to an interface downwards, and communication upward only happens by return values or eventually by callbacks. Another kind of high-level architecture is a client-server architecture where the client and the server each have clear interfaces and the communication only goes through the connectors that each of these interfaces provides. Some of these architectural description languages were developed as graphical tools. Here's one example called Vista. This was a visual scripting language that was developed as a prototype at the University of Geneva in the early 90s. And there were several other such graphical tools, like Conic Draw, which was developed at Imperial College in London. Write at CMU and also Acme were also similar visual languages that were based on the components and connectors paradigm. The one tool that came out of this that was actually a commercial tool was called ProGraph. That was a product of the 1990s. It still exists and now has been reborn by a company called Andiscotia, and the tool for Mac OS is called Martin. This tool still exists and is still available. So a prograph program is a directed graph of connected data flow components. So the meaning of the connections is that data flow will flow from one component to another. One tool that was kind of cool that was developed by Yahoo was called Yahoo Pipes, and it was also based on the components and connectors paradigm, where components are connected in a pipes and filters fashion. So each component has inputs and outputs. In this particular case, it can be used to script RSS feeds. So in this example, the dataflow script is filtering out blog articles from the PhD comics feed and only shows the comics and filters out the blogs. Yahoo Pipes existed for a little while, but it's now a defunct project since a few years. eToys is a good example of what's known as tile-based programming. So in the idea of tile-based programming, you have components which represent fragments of something that looks like a textual programming language with holes in them that can be filled. So you can compose programs by composing these tiles and filling in the holes. So this means that one doesn't actually have to write any text. Instead, one drags these components and composes them until we have a fully functional script. The script tiles all perform actions and provide commands for controlling graphical objects. So these graphical objects can be built in the environment and then they can be individually scripted. We'll see a few examples of these later. Another example, which is commercial, is OSX Automator. So this is a tool for scripting common actions as workflows in the Macintosh operating system. A very interesting project that dates from the early 2000s is called Naked Objects. Here the idea is that instead of coding all 4 tiers of a complex application by hand, instead both the persistence layer and the user interface will be automatically generated from domain objects. So each domain object comes with a graphical interface and also a persistence layer. So the idea is that in the end you're able to compose complex applications from these individual components. It's often contrasted to MVC, so Model View Controller, but the original developer of MVC, Trygve Reinskog, actually says in a preface to the thesis by Pawson, who developed Naked Objects, that this comes much closer to the original inspiration for Model View Controller. I encourage you to have a look at that. Over the years, all sorts of very unusual visual programming tools have been developed. One that looked very promising was called Subtext. This is a tool that encodes program logic as visual tables whose columns represent logical alternatives and rows are representing computational elements. Interestingly, the same tables can represent both conventional control structures, so if then else, as well as polymorphic dispatch. The tool is very example-centric. As you edit, the tables compute. There's a very nice video demonstration available on the website. Unfortunately, however, despite the initial promise, no public download was ever available. So it seems that the idea was very appealing and interesting, but aside from being able to run cool demos, there's no demonstration that it actually scales up to real applications. I mentioned earlier Pygmalion. AGG is the attributed graph grammar system, and it's based on the principle of graph grammars. So graph grammar is a formalism that, with the help of rules, allows you to take a graph of nodes and edges and apply rules to transform that graph incrementally. There's a demo which I'll show you that illustrates how a factorial function can be specified completely in terms of graph grammar rules. So what we see here is the attributed graph grammar tool, and we've loaded in a demonstration of the factorial example. The idea here is that we will represent the computation of factorial and intermediate states of the computation as graphs, and we'll be using a graph grammar to iteratively transform the factorial graph until we get a final result. In the graph grammar, there are two kinds of nodes that we have. We have factorial nodes and result nodes. So the factorial node represents a factorial that needs to be computed, and a result node represents an intermediate or a final result. And the edges represent connections between a factorial and a subcomputation that has to be completed. Here we see a host graph, and this is the factorial that we want to compute, a factorial for the value 6. On the left-hand side, we see a set of rules of the graph grammar. There's a recursive case, a base case, a computational case, and a final case when we're done. What we're looking at here is the rule for the recursive case. As is usual here, the middle panel here, this is the one that shows the subgraph that we want to match. So we want to match a case where there's a factorial node with some value n in it that needs to be computed. We're going to replace that by the node attached to a new node that computes factorial n minus 1. There are a couple of negative conditions as well. In particular, this one is the no recursive negative condition. It says there isn't already a factorial subnode, because if there is one, we don't want to create it. Second of all, there shouldn't already be a result node attached. And finally, we want to have the condition that n must be greater than 1. So this 6 must be greater than 1. This is the case, and we can actually apply this transformation step. So we apply it once. That'll generate factorial n minus 1. We apply it a second time. The rule doesn't apply here because we already have a subnode, but it will apply it there. We continue to apply it until finally we get factorial 1. And if we try to apply this rule again, it will fail because in all cases the negative preconditions fail. So every node is either attached to a subnode or n is equal to 1. Now we can go to the base case. So the base case is looking for a node where we have factorial with the value n equals 1. And we want to generate a result node whose value is also 1. We also have the negative condition that there isn't already a result node attached. Then we can apply it. If we try to apply it again, of course it will fail. Now we're finished with the recursion and the base case, and now we want to perform our actual computation. So the computation looks like this. There is no negative condition, but what we're looking for is a subgraph consisting of 3 nodes. There's a factorial connected to another factorial connected to an intermediate result. What we want to do is we want to grab these 2 guys and replace them by a single result whose value is going to be n times k. And now we can apply this, and we're going to match this subgraph here and replace these 2 guys. And that factorial 1 is, of course, has the value 1. Now we're going to compute factorial 2, and its value is 2. We'll compute factorial 3, its value is 6, and so on, until finally we reach factorial 6 is 120. We're not completely done. We want to get rid of that factorial node, and now we need this final step. This is looking for a factorial node connected to a result node, and the precondition in this particular case is that there is no factorial node connected to another factorial node. So we're down to the last factorial node. If we find that, we can throw away the factorial node and we have our final result. What we'd like to do is see how we can, how this looks if we apply all of the steps without applying them one by one. And we can do that. We simply set, for example, the expression to be evaluated to 10. And now we can ask simply apply recursively all of the rules until no rule can be applied anymore. So we'll start the transformation. And very quickly we get our expected result, which is the factorial of 10. Now let's try and take a step back and see what we can learn from this. There were several attempts to classify visual programming languages over the years, and in my opinion, they were interesting efforts, but they don't give us a great deal of insight into visual programming languages and their different variants. So Myers in 1986, this is quite some time ago, has factored visual programming languages into 2 by 2 by 2 quadrants. But as you can see, the splits are fairly rudimentary. So he splits them according to whether they're programmed by example or not, whether they're visual programming or not, and whether they're interactive or not. But doesn't dive into any further detail. Basically, the lower right quadrant are the real visual programming languages. So they're visual programming and interactive. Chang and Xu had a 3-dimensional scale back in 1987, but they are focusing more on visualization and not really on the programming aspect. And finally, Burnett in 1994 published an empirical classification for research papers. So this again is not visual programming languages, but it shows us where visual representations can appear in such a classification. So it seems like there's a need for a new kind of a survey and a new kind of a taxonomy, which should focus first of all on what are the visual elements. Are they going to be icons or graphs or tables or forms? How much text? Are they purely visual or mixed? For example, in the tile-based programming, the tiles are visual, but they are really representing textual fragments. Then what kind of paradigm is being used? Programming by example is one paradigm that occurs very frequently, but also constraint-based programming and data flow and tile composition. These are all different kinds of paradigms. The connector paradigm pervades many of these, so in many of these situations you have components which are connected to each other, but the connectors may mean different things. They may represent a constraint or data flow or simple invocation of a service. Third, what is the application domain? So we can see over and over again that visual programming paradigms seem to be very well suited to certain specialized domains, such as simulation or games, also animation. A more general domain, but still somewhat restricted, is that of modeling. So many models are graphically oriented, so having a visual programming tool to design and develop your models as opposed to writing them textually is also something that has been explored quite a bit. Algorithms seem to be successful up to a certain point, but they hit their limitations quite quickly. So certain kinds of algorithms are well suited for specifying graphically, but others are not. And finally, who's the target audience? Is it for teaching? Is it for beginners? Or is it more for a particular kind of limited domain or domain specialist? Now we'll have a closer look at eToys, which is one of the more sophisticated visual programming environments available based on tile-based programming. Here are a few references, in particular the articles on idioms for composing games with eToys will illustrates a number of particular tricks and best practices that you can use in eToys in order to compose more interesting applications. In a nutshell, eToys can be considered in the following way. First of all, the graphical user interface is the model. So there's no MVC. We just have so-called morphs, which are graphical objects that can be scripted. So this sort of flies in the face of the known best practice where you try and separate the user interface from the model so that you can flexibly glue them together. That can be very fine for complex applications, but if you want a visual programming environment, it's much more convenient if you actually merge together the objects with the behavior and their user interface. This is also one of the key principles behind naked objects. Furthermore, eToys, even though it's implemented in Smalltalk, it's using the morphic framework, which originated in Self, which was a prototype-based language. Self was a successor to Smalltalk that did not have classes, but instead was based on the concept of prototypes, the same model which was later used in JavaScript. As a consequence, the underlying graphical framework, the morphic framework, is also based on the idea of prototypes. So when morphic was ported back to Squeak, a successor of Smalltalk 80, the notion of prototypes, even though it's all implemented in Smalltalk, a class-based language, the notion of prototypes runs deeply through the morphic framework. Secondly, there is a notion of tile-based programming. So the only thing that you type are some names of scripts and some names of variables and objects. Everything else happens by drag and drop. So a tile represents a program fragment, possibly with some holes in it. So by dragging components into other components, you compose these tiles to form scripts. And these scripts control the behavior of the graphical objects. You also have a toolbox of existing objects that you can reuse. So these are prepackaged morphs with special behavior. We'll see some examples. And you can also compose your own morphs from the toolkit or program. If you want to, you can escape from the environment and develop new morphs in the Smalltalk language. The implementation of eToys is available from Squeakland. And there's also a plugin that allows you to run Squeak projects directly in your browser. But there is also a JavaScript version of Squeak.js, which has an implementation of eToys, which will run on your browser, everything being run under the hood with JavaScript. Squeak projects can be used to save the state of a set of objects, not just source code. So you can publish projects in such a way. And morphic objects in Squeak are entities that have so-called handles. So by right-clicking on a morph, any kind of graphical entity, you will see a bunch of handles that pop up that have various kinds of behavior. So, for example, at the top right corner there, we see the duplicate handle. If you click on this, you'll get a clone of the object. So this is the underlying notion of prototypes. If you click at the bottom right, you'll get a handle that allows you to scale the object in various directions. The top left, you can kill a morph by clicking the X icon. And as we'll see, the eye icon is the one that we use to script the behavior of morphs. Now I'll show you the canonical car demo. I'll just show you a couple of slides of overview, and then we'll dive into the demo itself. So in this demonstration, we're going to script the behavior of a car. So first we'll create a new morph representing a car that we'll paint. We'll be using the various morphic handles. I showed a couple of them to you already. So by right-clicking on a morph, you can change its name or access any of these different kinds of behavior. Particularly the eye icon is the one that interests us, that gives us a viewer for behaviors and scripts for the object. eToys allows you to script objects by composing these tiles. So by opening the viewer, you can see all the commands that is understood. So each command is accessible through this menu. We'll see that in the demo. And you can drag and drop the commands into a script in order to compose a higher level script. We'll use these commands to make the car move. We'll compose scripts from these commands. So those will be reusable sets of macros, essentially, of composed commands. We'll paint a racing track and make the car run along the racing track. In particular, we'll be scripting the behavior by looking at when the front of the car is leaving the racetrack. We'll try and turn it back depending on whether it's gone too far to the right or too far to the left. We'll try and adjust it so it'll run correctly around the racetrack. Finally, we'll publish the project. In this demo, we will see how eToys supports tile-based visual programming of graphical objects from the tiles consisting of commands, each of which controls some aspect of the object. First, we're going to start by drawing a high-tech car with the drawing tool. We make the front fender bright red so we can detect when it bumps against something. Adding some windows, and of course our car needs some high-tech tires. Beautiful. A car that we can race with. Now, in order to script it, we need to click on the eye icon, and this will open up the script editor. Here we see several commands that we can directly execute by clicking on the exclamation marks. We're going to create a new script, and this script will serve as a repository for various commands that we can drag into it. So here we drag this tile, which will move the car forward by a certain number of steps that we can control, and will also cause it to turn. So when we can not only play this, but we can also set a clock ticking, so it will repeatedly run this command. Now we're going to draw a racing track for the car to drive along. We're also going to make the center area nice green grass so we can tell when we veer off the edge of the road. Now we're going to modify the script so that we can detect when the red fender sees the green lawn, and it'll adjust its steering back to the right. So when the car's red fender sees the particular green of the lawn, we're going to turn the car in an appropriate direction. And we'll have to fiddle with this amount in order to make sure that we don't overshoot. Similarly, if we see that we're running off the other side of the track, we'll also turn the car going back in the opposite direction. Now, by fiddling with the variables, we can get slightly better behavior of the car. In this demo, we're going to do something a little bit more advanced, which is the implementation of a state machine using eToys. In this demo, we're going to use eToys to develop a very simple state machine simulator. First, we're going to clone a pin object from this toolbox that we can use to build state machine graphs. We're going to change the colors of the state to make it look like a more classical state node. We now open the script editor to script a bunch of higher level commands that we need to model the behavior of state machines. We first implement two simple scripts to turn the state on and off, toggling the color between black and white. Now, we also need to keep track of which states are enabled as the possible successor of the currently active state. So we introduce a new variable called enabled, and this should be a Boolean variable. We similarly create two command scripts to enable and disable a state. We can now clone this scripted state and connect the two of them. Now, for the simulation, we need a script that reacts to mouse clicks. If we click on an enabled node, it should become the current node. This should turn off the current state and turn on the clicked state. So if a state node is enabled, we will tell all its predecessors to turn off. This will include the previously current state. We also turn ourselves on. If, on the other hand, the current state is not enabled, we'll give a warning noise. Now, when a node becomes the current state, it should enable all of its successors, so we adapt the turn on script accordingly. By the same token, when a node is turned off, then all of its successors should be disabled. Now what we've done is we've just scripted the node that's on the left-hand side. So the node on the right-hand side no longer has this behavior, so we should throw it away and clone the node that we just scripted. Now we have two nodes with the same behavior. So now we're able to create state machines by cloning these pieces. Let's create a little tool, a button bar, which will make it easier to clone these graphical elements. So we pull out 3 maker buttons, and each of these maker buttons will correspond to one of the 3 graphical elements that we have. We drag the three maker buttons into the button bar, and now we have our complete application. Another example of a kind of sophisticated tool that you can build with eToys is a PetriNet interpreter. So in this case, here we see an example of a simulation that's been built with the Petri tool, and this represents dining philosophers. So each of the entities that we see here are actually morphs. So we have morphs representing the places, like this one, and we have morphs representing transitions between places, and we have the connectors between them. So in this particular case, we're modeling dining philosophers. The yellow places are the ones representing the forks. The collection of places highlighted in blue represent philosophers. So a philosopher here wants to grab the left fork first and then grab the right fork, then it will eat, and when it's done it will replace both of the forks. We've connected all of these together here, and unfortunately in this particular case, if every philosopher grabs the left fork first, we'll get a deadlock. There are various idioms within eToys which are particular to eToys itself that make it easier to build applications. These are described in the paper that I referred to by Marcus Gelli. So here are a few examples of different kinds of games. Here's the Lights Out game. The Lights Out game starts with a grid with a bunch of lights which are all turned on. As we can see here, the lights that are all white are turned on. But every time you click on a light to turn it off, it will turn on all of its neighbors. And the goal of the game is to manage to turn off all of the lights. So this requires some strategy. The game can be implemented quite nicely in eToys by composing a bunch of clickable morphs. But in order to encode the knowledge of which lights are connected to which other lights, a little trick has to be used. So we encode the neighborhood relationship between objects by letting them overlap. So notice each light is not exactly a square, but kind of a rounded square. And they are close together so that they actually overlap slightly, but not at the corners. So that means that this particular node here will have neighbors to the left, to the right, above and below, but the diagonals do not overlap. And as a consequence, you can use the overlapping relationship to control the scripting behavior. Another idiom used in eToys is known as visual cursor, and here the trick is to store the selected element of a playing field in a particular cursor object that keeps track of certain information. Here we see the 15 puzzle. So the 15 puzzle, as you know, you have to keep moving these squares around until all of the numbers are in the proper order. So actually we want to get 13 up here, we want to get 10 up here and 11 and 12. So that should be pretty easy to do. But the trick is how to implement the game. So the 15 puzzles cursor object keeps track of the current empty cell, which one that is. So that's this one here. If a move is legal, so we can click on 8 or 12 or 15, but on none of the other squares, then the number is transferred to the empty cell. So if I click on 12, the 12 will move here. But if I click on 6, it's not adjacent, so it won't be able to be transferred. Then the click cell becomes the puzzle's currently empty cell. Another common idiom is known as intelligent environment. So here we have an X and O's game, a tic-tac-toe game. And in order to script the whole behavior, we need to keep some information around in the environment. And these are these hidden objects in the background. These are the so-called stone counter objects. So these are the ones whose responsibility it is to check whether there are 3 in a row. So we have 3 for each of the columns, 3 for each of the rows, and 2 for each of the diagonals. And these stone counter objects are hidden in the background. Here we see them, they're made visible for us, but they're the ones that are going to be doing this background information. Stepping back a moment, what do we learn from eToys? So there are several good aspects. The idea of unifying the graphical user interface and the model is very powerful. It's especially useful for these kinds of applications where we're building simulations or animations or modeling tools. The paradigm of composing tiles is extremely powerful. It's a little bit annoying at times because you have to find the right tiles. So sometimes you wish you had keyboard shortcuts, but it's for these kinds of applications, it's quite convenient. There's a rich toolkit of existing components which you can reuse. And the prototype-based paradigm is very nice and encourages exploration. We have variables that are typed by example, booleans and strings and other values. And what we didn't talk about is that Smalltalk is generated behind the scenes. It's quite expressive, so you can do all sorts of things, not just animation. So the fact that you can build a fully fledged PetriNet interpreter is a good demonstration of the power of eToys. On the other hand, the interface between eToys and Smalltalk is quite opaque. So when you hit the boundaries of what eToys can do, trying to extend it by programming some new behavior in Smalltalk is not so easy. The kinds of events that the morphs can understand are quite limited. You cannot extend that easily as well. There are some notions that are missing, like matrices. You have to build these up by hand. So we had a couple of examples of games that were based on matrices, but they can be a little bit clumsy to program. Projects are stuck in an older version of the Squeak environment, which is a bit of a limitation. There are no arithmetic expressions built in, there's no debugger, and the command structure is kind of strange. Also, scripts don't return anything. And on the ugly side, in this version of Squeak, the eToys code is deeply merged in with the Smalltalk Squeak implementation. Another tool that was built after eToys looks much more professional and more sophisticated is called Scratch, and it has a rather different paradigm. The paradigm is that of communication by broadcasting. It's also tile-based, so it provides you with a large number of, here, a bunch of different categories of tiles, so tiles for motion, look, sound, and so on. And as you click on these, you'll get different kinds of basic components available. In this area, you write your scripts, so you can drag and compose these tiles just as you do with eToys. And then in this pane here, you can make drawings which are then controlled by the scripts. Scratch is really designed for building animations, and it does that very well, so it's excellent for teaching kids a little bit of programming, but it's quite limited. For example, it's impossible to implement the PetriNet interpreter in Scratch due to the underlying broadcasting model of communication. Okay, that concludes today's lecture. We've seen quite a lot of different tools and different kinds of visual programming paradigms. Visual programming keeps popping up over and over again over the years, but frankly, I must say that the level of maturity of visual programming tools is rather limited. What you can do with it is usually works best when you're focusing on a particular application domain. So dedicated visual programming tools, for example, for UML modeling or for teaching kids or for building animations or simulations, works very well. But as a generalized programming paradigm for writing all-purpose programs, visual programming is not yet there. Thanks again for your attention.